In this chapter, we're going to learn about nuclear magnetic resonance, NMR, as it's typically called. A typical NMR spectra looks just like this one for this compound, and the power of NMR is that it gives you the individual hydrogen peaks of a compound. And again, this is a hydrogen NMR. And so it's really a powerful technique because, again, it gives you the carbon-hydrogen framework. It gives you a tool to depict that. How this technique is more powerful and different, let's say, than something like IR is consider that we have this alcohol. It has 1, 2, 3, 4 carbon groups, has an OH group. Let's say we had a sister alcohol, this one. Again, it has 1, 2, 3, 4 carbons and an OH group. An IR spectra of each one of these will look virtually identical. There'll be some small, subtle differences, but for the average student, you wouldn't be able to tell a difference between these two and an IR. Alright, so IR is what we have learned about. However, these two would look radically different in an NMR spectra, and we could tell the difference of where the OH is and how these carbons are arranged. And that's really the power of NMR, nuclear magnetic resonance, and here particularly we're talking about hydrogen NMR. So let's talk a few things of what we know. So really, what is spectroscopy? And a spectroscopy, again, as we see here, is a technique for analyzing the structure of molecules. For IR, this was sort of the functional groups. For NMR, this is its carbon-hydrogen framework. Now compare that to some other tests you've done for your unknowns, things like melting points, we might have done a boiling point, density, calculating or estimating molecular weight, and intermolecular forces. All right, those are all real physical tests. Well, it turns out that spectroscopy is one of those tools, except it's a little bit different than the physical test that we talked about. And again, it gives us a chance to really look at the structure of these molecules. These three, NMR, which we'll learn about today, IR, which you've learned about, and UV, which someday you'll learn a little bit more about. This all deals with electromagnetic radiation and helps us determine the structure that way. Mass spectrometry, or spectroscopy, is built on a different technique than these three. These are all basically, I'll just call it electromagnetic radiation. All right, so light like radiation, mass spec, MS is a little bit different. The nice thing is about NMR is that it really is one of the most powerful techniques because, again, it provides detailed information regarding the atomic connectivity of a molecule. So the difference between the two alcohols that we saw on that first page. In IR, NMR, and UV, these are all built upon electromagnetic radiation and electromagnetic absorbance of that radiation. And so remembering back all the way to chapter 6 in Gen Chem, all right, where we learned about waves. All right, so again, the frequency nu is equal to the speed of light c divided by the wavelength lambda. All right, so again, remembering that the speed of light is 3 times 10 to the 8th meters per second, and frequency is usually given in terms of hertz or inverse seconds. All right, and so each one of those techniques, NMR, IR, and UV, just uses different wavelengths of light. All right, and so the result is that different wavelength of light has different energy, and so that is important in terms of understanding more about these molecules, because we understand that molecules will absorb this electromagnetic radiation in discrete quanta of the energy molecules. All right, and so because they absorb this discrete quanta, or this discrete photons, it's really measurable by spectroscopy, and we can tell much about their structure. All right, so just to continue on that thought, again, the idea that these molecules are absorbing this discrete packets, which we can call quanta. Quanta are also called photons, and in a lot of ways we can use those two terms interchangeably. All right, so again, the amount of energy, the packet of energy that molecule absorbed is called a quanta, which we can also refer to as a photon. And then when we talk about it as a photon, we can measure its energy, and energy is equal to h, which is Planck's constant, times the frequency. Remembering, of course, as our figure 10.1 from the book shows us, is that as a molecule is in the ground state, Alright, so, and then it gets hit with some of this energy, and it could be UV or IR. The NMR, it basically becomes into the excited state. Alright, and so we can have techniques to observe this absorbance of energy to the excited state, but then also in some cases the falling back down from the excited state to the ground state. And all of those are really quite important, and because we can observe the ground state, the excited state, here or potentially there, depending on the technique, that just allows us to see into the structure and into the makeup of these particular molecules. Let's follow that up and take a look at a few techniques and how they relate to the types of radiation that is used. One technique that we've not talked about, and we'll probably not talk about it in this class, is X-rays. But you may have heard of X-ray crystallography, where you're able to get the structure for organic compounds and like proteins, and that uses X-rays, and those really result in the promotion of inner shell electrons. Alright, so here are X-rays. Notice that they are really small wavelength compared to the rest of these, and they're also fairly high energy. Alright, so X-ray is really short wavelength, high energy, and they're able to absorb and sort of promote those inner shell electrons. If we move a little bit to the right on this spectrum, again noticing wavelengths down here, we get into UV and visible. And this is, of course, the visible range we can see, and then ultraviolet rays, which we've heard about before from the sun and those types of things. UV-vis, they cause the excitation of valence electrons. Alright, so to move those. So one of the reasons, for instance, that we often wear sunscreen in the summer to protect from UV light, and that's because UV, higher energy, alright, so again, closer to this direction to X-rays, and they can actually start to move electrons around, so potentially molecules in our skin can become damaged by absorbing too much of this UV light. Alright, and so, but nonetheless, it's those valence electrons, those in the outer shell. Alright, so we can continue to move on to IR. Here's IR. And IR bonds, IR radiation, they cause bond vibrations, and we've seen this in IR, how alcohol groups and CH3 groups, how they have different absorbances, and they would be somewhere in this range of NMR. Alright, so they provide those. Microwaves, again, noticing we're getting longer wavelengths, so we're actually decreasing the energy. Microwaves aren't nearly as strong as any of these, so they really can't cause bond vibrations or anything along those lines, but they can cause whole bonds to rotate and really molecules to rotate. And so that's why we use, for instance, put water in a microwave, and it really causes them to really start spinning faster and to heat up. Alright, so again, not as high of energy, longer wavelength, but nonetheless it can still cause molecules to do something. And that brings us to radio waves over here. And that's where NMR comes in, is that radio waves in a magnetic field, they can produce nuclear magnetism, and they can make nuclear spins align. Back to our figure from the very first slide, the spectrum of a typical organic molecule and what it might look like. Alright, so as we're going to see as we go through and learn a little bit more about NMR, we're going to get really 4 pieces of information. As we look at these spectra. Number 1, we're going to get the number of signals. Alright, so in this case, we're actually going to have 1, 2, 3 signals. Notice that this one right here is what's called a reference peak, and this is known as TMS, tetramethylsilane, and this is a reference. This helps the standard. So that helps us basically say that this is 0, but these are the 3 signals, and ultimately those 3 signals tell us how many different types of hydrogens are available. So first of all, we get the number of signals. Number 2, we get the integration. Alright, and the integration simply tells us how many hydrogens, in this case 2, and 1, and 3, are under these peaks, under the area of those peaks. Alright, so that's important because we can get the number of hydrogens that are present. We can also get the chemical shift. Alright, so this is the chemical shift, this axis here. Notice it's in parts per million, but notice this one absorbs at about 0.85 or so. This one's what, about 1.8. This one's 3.2 or so. And basically where they absorb on this scale is known as the chemical shift, and so that tells us some information about those molecules. And then finally we get something known as spin splitting, all right, and that gives us some information about the connection of these peaks. And we'll notice that this spectrum right here that we're looking at does not have this spin splitting, but that becomes more important as we go along. All right, so NMR gives us information about the alignment of these nuclei. All right, so and as a result, we get the number of signals, the integration, chemical shift, and the spin splitting. Let's delve into this a little bit more and see how we get these 4 bits of information. So in a magnetic field, and we call that magnetic field HO, hydrogen 1 NMR, their spins align either with, which we call alpha, or against that field. All right, so they line up with it. So again, they're in a magnetic field, so they're basically put a sample inside of a magnet, and then because they're in a magnet, their spins, the hydrogen spins, they're going to align either with or against the magnet. All right, and so that's important. So what do we, first of all, let's break this down just a little bit. First of all, we say hydrogen, and basically when we are talking about NMR in our class, we're going to be talking about hydrogen 1, and so this one absorbs. Also other atoms, such as carbon-13, and let's see, nitrogen-14, those would also, the spins of those would also align with or against the magnet, and it's because they have an odd number of either protons or neutrons. All right, and so that's why carbon-12 would not work, because it's 6 protons and 6 neutrons, but carbon-13 does. And for nitrogen, it has 7 protons and 7 neutrons, and so it would. So basically, if we have both even numbers of protons and neutrons, like carbon-12 or oxygen-16, that would not work. All right, so in this case, hydrogen-1 does work. However, deuterium, H2, would not. All right, because ultimately it ends up with an even number. So that's important. So number 1, it's a spin. Number two, what is it about this spin? Well, hydrogens, they're spinning because they have an odd number, and they actually have a pole, and so they're always constantly spinning. So if you can imagine, they're sort of spinning like a little child's toy top. If you spin it, it sits on the table and spins a while. All right, so it's sort of spinning in that direction, let's say, just going around. And so nuclear spins sort of have this pole, much like the pole of the Earth or something, and they're constantly spinning. All right, and if you would have a whole bunch of them, all right, their spins would be all over the place. All right, so we would just put them. So if you had a whole bunch of hydrogens, however, if you stick them into a magnet in a magnetic field, these guys would either line up with, we'll just call this the HO. They would line up with the magnetic field, which we call alpha, or against it. All right, they go in the opposite way, which we call beta. All right, so these 2 are alpha, these 2 are beta. And because in this magnetic field they do that, they either line up with or against the magnetic field, that we can actually then tell something about them and also observe that signal. And by the way, if it's alpha and it's lined up with a magnetic field, that's of lower energy, all right, and so the beta then is a little bit higher in energy, all right, so we'd actually have to give energy to the alpha ones to get them into that beta position. All right, so, and how do we do that? Well, radio waves, they can flip the hydrogen from the alpha, lower energy, to the beta, higher energy. All right, so we can actually add some energy in, and we can get these alpha to flip, turn over, so they're actually, their spin's pointing down. And that energy difference between the alpha and the beta, so going from a lower energy to a high energy, is what we know as resonance. All right, so this difference in energy and flipping them is what we say that that's resonance, and that's an important term in NMR. All right, so that's that difference between the alpha and the beta proton spins when they're in a magnetic field. And the fact that we can put energy in the terms of radio waves and flip them from the alpha to the beta and detect that allows us then to tell us something about the structure of molecules. We find that hydrogen nuclei in unique structural environments, they tend to absorb characteristic frequencies. All right, so we can actually have different radio waves, just like different radio stations, and you can actually pick out which of those radio waves are absorbed by, say, a certain set of alpha to beta, because we're going to find out not all of the hydrogen nuclei act the same. And as a result, we can pick out different types of nuclei. So in this particular molecule, which is just chloroethane, so one chloroethane, but just chloroethane is what we would call it, we actually have two different types of nuclei. All right, so we have A here, and it's because this both of these hydrogens are connected to that carbon, which is connected to a chlorine in that one, and so those are one type. The A are one type, and then these three, which we have labeled B, these are three other hydrogen, and they're different types. We would say that in this compound that we ultimately have two types of H1 nuclei, and so in a magnetic field they would absorb different amounts of energy to flip their nuclei from alpha up into the beta, all right, the beta resonance, so that resonance energy would ultimately be different. All right, so that's important. And so just so again, we have these two different types. By the way, just so we bring out this term, we would say that type A and type B, they are what we say are chemically equivalent. Probably shouldn't use red since I've already used that. We'll just use black. So chemically equivalent is the term that we want. All right, so these two A's are chemically equivalent, all right, because they are basically both attached to a carbon, which has the same other connectivity, so we would say A's. These two are chemically equivalent to one another. These three B's are also chemically equivalent, all right, so because these two are chemically equivalent and these three are, that ultimately gives us two types, which we've labeled here just A and B. And within their little groups, however, we would say that they're chemically equivalent, and so as a result, those give us two different types of nuclei. All right, so compare that let's just compare that to straight ethane. In ethane, all 6 of these hydrogens would be chemically equivalent, right, because they would all be in the same environment. Each hydrogen is connected to a carbon that's connected to another carbon with 3 hydrogens. All right, and so there's, and it also has symmetry, which has a little bit of impact, but basically just shows us that we have just one chemically equivalent type of hydrogens. All 6 of them are the same. We'll go just one more. All right, if we take propane, propane would have 2 different types. Like I was going to say, like this first one, they would have 2 different types. All right, can you pick them out? Well, one set, I'll just label them A, there's a blue here, and so the hydrogens on each end, all right, those are chemically equivalent. And then the 2 hydrogens in the middle, which I'll call B, those are also chemically equivalent. All right, now the B's are different than all of the A's, and so that's why we call them chemically equivalent. And then all 6 of those A's are chemically equivalent, but they're different than these B's. All right, so hence in a NMR, that all 6 of these A's would show up at the same spot, and these 2 red B's would show up the same spot. All right, so that allows us to pick out different types of hydrogens in a molecule. Now, where these groups absorb, we can find this in a table. In our textbook, it's table 10.2, and that can show us where where they absorb, and that's the second bit of information, the chemical shift. And so notice we were talking about ethane and propane. Well, notice that the primary alkyl groups, also on the end, they would absorb between 0.8 and 1. The secondary, like in propane, would be in the middle, be 1.2 to 1.4. All right, so that's important, and you can see some of the other characteristic shifts. Chemical shifts for various functional groups that occur here. I should point out you do not need to memorize this table, but you should be able to recognize the table and also be able to pick out, like say, an alcohol peak. Well, it's actually a CH2 connected to an alcohol, and where it actually absorbed. Here is an alcoholic hydroxyl group, ROH. Notice it's sort of, some of these are variable. And so these chemical shifts, again, once again remembering, are the positions where they absorb on this scale here, which is in units of parts per million. And this nicely sort of gives you some saturated ones. Here it shows you where if you have some electron withdrawing groups like chlorine, aromatic groups are here, and aldehydes are there. All right, so we see those. Couple of things to point out. This is our 0. This is sort of the beginning of this. Remember, this is on a previous one. There was the TMS, tetramethylsilane. Generally, if we move in this left direction, we're going to refer to this as downfield. All right, so downfield. And if we're more moving in this way, we're going to call this upfield. And it has to do with some older terminology that chemists use, but just know that going to the left is more downfield, or we might say, that this is downfield of this one, but we might also say that this group is upfield from the aromatic group. All right, so that's important. This chemical shift, this parts per million, this delta here, is in units of parts per million, and this is a way to give us a field-independent measure because different people have different sized NMRs. They would show up at different places. However, if we have the distance of the peak from the TMS, which would be here, and over the frequency in megahertz, then that gives us a units of parts per million. And then anybody using any type of NMR, it would all show up in the same place. All right, so let's bring in our figure again to point out, and this is one we saw at the beginning and now here. And so again, remember we were pointing out that different chemical shifts, so this CH3, right? Remember this is sort of a primary one that comes at about 0.8 to 1. Notice that's exactly where it is. The OH group, all right, so 0.5 to 5, so it has this whole variation. This one's about 1.8 or so. That works. And then you have this CH2. Notice that CH2 is next to an alcohol group, and so it's this one. And so it's in that 3.3 to 4 range, which is about exactly, just about where we get it. I think I said 3.2 earlier. All right, but nonetheless, these are the chemical shifts. All right, so one, we got the number of signals. We can also get integration. We can also get chemical shifts. All right, so here we know about the integration, the area under the peaks, and now we've gotten chemical shifts.